My name is Sherrie, and I'm a fifth-year PhD student at Stanford. And today I'm going to talk about a meta-learning for remote sensing, which is, we were just talking about transfer learning in the previous talk, and this is one way to explicitly optimize a neural network for transfer learning. So this is a work with Mark Roosboom, who's at TU Munich. Mark is advised by Marco Kerner at TUM, and David Lobel is my advisor at Stanford. So the reason that Mark and I were motivated to work on meta-learning is because both of us have worked on crop mapping and crop type mapping over the last few years throughout our PhD. And we have been doing this all over the world. I've been working mostly in the US, and Mark has been doing a lot of work in Europe. And I've also done crop mapping in India and in parts of Africa. And what we noticed was that every time we go to a new location and we want to perform some sort of crop classification, we basically start from scratch. Even though if you observe cropland all over the world, you notice that certain traits are shared across regions no matter where in the world you are. So here we're showing 4 examples from Brazil, Poland, Mali, and Angola of cropland. So you'll notice that, yes, the background vegetation looks different in each place. The size of fields can be different, but you still have similarities such as the fact that crop fields are, for the most part, rectangular and very regular in shape, as well as the fact that crops, they tend to grow over the course of the growing season and then senesce, or AKA die or are harvested. So over time, they also have many characteristics in common. So traditionally, what we've tended to do when we do crop mapping is in each region that we're working, we'll take whatever data we have in that region, for example, Brazil, and we will train a model just on that data set. And then if we wanted to go and do some crop mapping in Poland, we would again take whatever data we have in Poland and train a new model there, ignoring the fact that we had any data in Brazil. And when we do this, we wouldn't expect a model that we train in one region to generalize to another region because they're quite different. And in fact, we do observe that when we try to just directly apply a model trained in one place to a different place, often that model just breaks down completely, and the performance is no better than random guessing. Another thing that people in the field of land cover classification often do or can do sometimes is group all of their data into one big data set and then train one model on all of this data to perform classification. And this can result in better performance if there's what's called positive transfer between regions, which is another way of saying if figuring out how to classify crops in Brazil helps you also classify crops in Poland. But the downside of this strategy is that your model parameters are completely shared across regions. And so it's not ideal for if you want to add a new region to your data set, like suddenly I want to do crop mapping in China, then I would have to retrain from scratch this entire big model again. And also if you have an unbalanced set of data where certain regions have a lot more data than others, which is the state of the world that we currently find ourselves in, then the model will be incentivized to do better on the regions with more data. And that may happen at the expense of regions with less data. And so the underlying machine learning problem that we're dealing with here, which folks have already covered in previous talks, but I'll just state here with a simplified picture, is that the distribution of the training set and the distribution of the test sets often are not, they're not the same in our applications when we try to go from one region to another. So in the top panel here, we're showing if it's true that your distribution on your training set is identical to your distribution of the test set. Then when you learn a decision boundary on your training set, the test set follows the same data distribution, and so your learned decision boundary applies well to the test set. But when this is no longer true, when your training set and your test set are not under the same distribution, and here we see that the test set has undergone a rotation relative to the training set distribution, then when you take the decision boundary that you learn on your training set and you apply it to the test set, the classification performance goes way down. As you can see here, there's going to be a lot of misclassifications of what's in the blue class and what's in the orange class. So tying this back to our particular application, we see that as we move across the Earth's surface, the representations of imagery across the Earth's surface is going to change dramatically from region to region. The plot that you're looking at here is when we ran a bunch of imagery from 4 regions across the world through a VGG16 network that was pre-trained on ImageNet. And then we took one of the last layers of the ImageNet, of the VGG output, and then we used that as a feature vector for these images. And then we conducted PCA across all these different images, feature vectors, and then we're graphing the first principal component against the second principal component. So here, you can basically see that these different regions images cluster, and as you go from region to region, the features are shifting across this 2-dimensional space. So this is another way of saying that basically images from Mali look more similar to each other than images from, say, Poland on average. And then if you imagine training a classifier on Mali data to, say, classify 2 different crop types, and let's just say that decision boundary goes through this cloud of black points, then if you were to apply that decision boundary to the imagery in, say, Brazil, over here, the cloud of blue points, then that decision boundary is not going to generalize to data from Brazil. And so your classifier can't transfer to a different region. So instead of trying this direct transfer, we're going to explore a set of methods called meta-learning. And under meta-learning, the model is learning how to learn. So to explain what that means, I'm going to contrast that against 2 types of learning that people may be more familiar with. So the first is single task learning, which is the case where, let's say you have an agent and you want it to know how to hike and walk and ride horses. Then you're going to treat all of these tasks as individual tasks and then just train a model from scratch on the data that you have for each one. So that's analogous to the first strategy that I brought up a few slides ago, where in each region you train on the data set that you have in that region, and there's no transfer between regions. The second strategy is known as pre-training and fine-tuning. So this is starting to move into the realm of transfer learning, but it's still a relatively simple transfer learning method. And under pre-training, you have the set of tasks that you want the agent to learn to perform, but really you're after one of those tasks in particular. For example, here, you want the agent to learn how to hike. So you pre-train on a bunch of different tasks because, for example, you think that learning how to walk is going to help your agent learn how to hike. And then the fine-tuning portion of this is when you refresh your agent or your model on the task that you're actually interested in this case, hiking. So this is analogous to pooling a bunch of different regions together, and then you might fine-tune on one of the regions that you actually care about. Under meta-learning, instead of doing treating the regions or the tasks as totally separate or just grouping them together, you ask the model to observe data from each of these tasks and then learn how to learn each task. So for example, it might absorb data on how to hike and how to walk and how to ride a bike. And then it's trying to learn the best way to learn a new task from the data that it's observed. And then the end goal is to be able to quickly learn a new task, such as ice skating, that it's never seen before. So that's all pretty abstract. So I'm going to talk about the specific algorithm that we look into, which is one of the most well-known and most commonly used meta learning algorithms. So this algorithm is called model agnostic meta learning. Model agnostic because it can be used with any neural network architecture that you have. You basically just need something that is trained using a gradient descent based algorithm. And so what model agnostic meta learning, or MAML for short, is doing is it's taking a model that's initialized with, I'm representing it as theta here, and it's going to adapt the model to each task that you have. So here I'm showing 3 tasks in this loss landscape. And for each task, you sample a set of data points, and then you use gradient descent to adapt the model theta to each task, which we're denoting with the phi's here. So phi 1 is the adapted model for task 1, phi 2 is the adapted model for task 2, and so on. And then you look at how the adapted model did on each task, and then you go back to your initialization and say, how can I make the initialization better so that when I adapt, the adapted versions have better performance? So there is not only gradient descent during adaptation, which is the first order gradient descent, there's an additional layer of gradient descent on the initialization theta. So this actually involves computing second order derivatives. So if we look at what actually happens when we adapt theta to different regions around the world, we see that, again, we're doing a principal component analysis on the parameters that we get so pre-adaptation here, theta as the black star, and then post-adaptation in 2 different regions, 2 different countries in the world, Poland and South Sudan. So you can see that, so there's a distribution here because it's a bunch of different tasks with slightly different sampled data. And you can see that the Poland tasks cluster together and the Sudan tasks also cluster together. So there's some structure here in the space of neural networks where adaptation is leading you to a set of networks that work well in Poland and a set of networks that work well in Sudan. So applying MAML to the land cover classification task that we've been talking about means that we're going to treat geographic regions as meta learning tasks. So before we were talking about hiking and skiing and riding horses, and instead of that, we're going to have task 1 be, say, trying to classify cropland in Mali, task 2 trying to classify cropland in Brazil, and so on. And you can see they may have different distributions, but you're trying to train models that learn, once it sees a new distribution or a few samples from a new distribution, how best to adapt the initialization to this new data distribution quickly. So we did 2 experiments. Actually, we did quite a few experiments, but I'm going to talk about 2 today. They both have to do with image-based land cover classification. One is on the Sen12MS dataset, which uses Sentinel data and is a global data set. It's multispectral and it's moderate resolution. And then the other one is the Deep Globe dataset, which is more local. We don't know exactly where the data and what the imagery is coming from, and I'll talk about that in a second. It's an RGB and it's super high resolution at 0.5 meters. And the task that we're going to do for Sen12MS is image classification, and for Deep Globe, it's going to be semantic segmentation. So we chose these 2 different data sets to span moderate and high resolution, and also different types of spectrum. So for SEN12MS, we're asking the model to perform image classification. So here I'm showing examples from the first, say one particular task in one region. We have one class, which in this case is forest. So even though there's a kind of segmented label here, what we did was we took the most common class in the label. So in that case, this is forest. And then say class 2 here is, for example, croplands. So we're asking the model, here's an example of an image that I'm telling you is a forest. And then here's an example of an image that I'm telling you is cropland. And then I'm going to show you more images from these two classes, and I'm going to ask you to place them in the appropriate class. So that's what the support set and the query set denote. The support set is analogous to the training set in single task learning, only that we are calling it support to differentiate it from the meta training and the meta test set. So the support set is the set of data that you see within each task that you're asking the model to adapt using. And the query set is the set of data that the model gets tested on for each task that then you're using to adapt the to update the initialization of the model. So when we compare MAML against pre-training and random, here is, we mean a random initialization of the model, so basically training from scratch. We see that MAML is able to adjust to new distributions with just one shot, which refers to one example from each class that is trying to classify. Whereas, yes?
Do you have about 2 more minutes to wrap up, 2 to 3 minutes?
Oh, okay. Thanks. So you see that basically above one example for each class, MAML is outperforming pre-training and training from scratch. Though you can also see at 0 shots, it's doing worse than the 2. And that's because it's not explicitly trained to do well when it doesn't see any data at all. So for Deep Globe, I'll just go through this quickly, where basically we have these very large high resolution images, and we're telling the model, I'm going to show you small patches of the image, and then I'm going to ask you to segment half of the image that was not part of your support set. And here, what we see is that if we split these images in a way that makes the training set and the test set different from each other, then let's just focus on the panel on the right. Basically, MAML is outperforming pre-training and a random split when the training set and the test set images are sufficiently different. And here I'm just showing one example of the case where MAML is doing pretty well when it gets to see what's in this red box, and then it has to predict the rest of the image here. You can see that it's capturing a lot of this magenta class that pre-training and training from scratch are not able to do. So to conclude, this application is not directly in weather and climate, but we're showing that basically meta-learning applied to the domain of remote sensing data can help us do better, at least than pre-training and fine-tuning on data distributions that are very different from your training distribution. And so the hope with this work is that we can open up a new direction toward creating general models that can operate anywhere on Earth with just a few training samples. There's a lot of different meta-learning algorithms. There's a lot of progress that's been made in this field, so there's still lots to be done to explore how meta-learning can help us create general Earth models. So with that, you feel free to email us or contact us for more information about the experiments that we did, or check out the paper that we published in CVPR about it. Thanks.
Excellent, thank you. So with that, why don't we take questions first for Shay? So one question that is here is, Shay, does the resulting MAML model result in better representation of key features in the neural network?
Better representation of key features. I guess I'm not totally sure what the question means. Could you clarify a bit?
My guess is that it goes in the direction of, often we say in meta learning that like earlier layers get most of the information then, and you only have to retune the later layers. So the earlier ones probably have better feature representation.
Oh, I see.
Is that the case in MAML as well?
Oh, yeah. So we didn't look at explicitly what were the filters learned in the convolutional neural network, but we did do experiments where we made the learning rate of each layer learnable. So instead of updating the entire neural network with the learning rate of alpha, we're saying every single layer of the neural network can have a different learning rate. And we're going to meta learn those as well. So what we saw there was that the learned learning rates of the last layers of the network were quite large, and the learned learning rates of the early layers of the network were relatively much smaller. So that suggests that during adaptation, it's very important to adapt the last layers, which have to do with which classes you're classifying into. That's more critical for adapting to a new region than maybe some of the very early layers, because again, some of the very early layers, like you mentioned, share a lot of features, like just trying to pick out different features of a landscape.
Great. Another question also to Shay. Can you fix errors in identification? For example, if the pixel is actually mixed cropland, could it identify a data set not included in the support set?
I see. Yeah, so actually, yes. Basically, what happens is you train the neural network to have an output that is you have to say that the network output is going to be a certain size, at least the way that few-shot learning is currently structured. So you might say, I'm going to do classification into 5 different classes, or you can do classification into 2 different classes, whatever it is. But those 5 can change from task to task. So you can say in task 1, I'm going to differentiate the 5 different crop types that exist in the US, and then in task 2, I'm going to differentiate the 5 main crop types that exist in China. So yes, meta learning is set up to be able to do those sorts of tasks, and you can train it to do that.
All right. We have one more quick question for you, Shay, and then we turn over to the overall panel. The question is, what is the difference between meta learning and multitask learning?
Oh, that's a good question. I took a class called Deep Multitask and Meta Learning. So they're different. So multitask learning, you're training on a bunch of different tasks, and you're hoping that there's some, again, positive transfer among them. So training on all of them at once will help you do each one better, or at least the one that you care about better. So the training happens for that set of tasks, and you care about that set of tasks. For meta learning, you also have a set of tasks, but you're training on that set of tasks to do well on a new task that you've never seen before. So multitask learning is not explicitly being optimized to do well on a new task, though training on K tasks may do better on a new task than training on one task, but it is not explicitly being optimized to do that, whereas meta learning is saying, when I give you a new task, figure out how to do that well.
All right, thank you very much.